integrating functions of time. Let's take a look at what this means graphically and how we can use the graph to solve problems. So we've got a velocity time graph here. Now we know the change in displacement will be the complete integral. So if I want to know the change in displacement during the first 4 seconds, then I would integrate from 0 to 4. So displacement is the same as the integral. Whereas if I want the change in distance, that would be equivalent to finding the area. So I would have to split this particular one up. 0 to 1 is above, 1 to 3 is below, so we got minus that one, and 3 to 4 is above, so it's also positive. So acceleration, we can use the same idea. Change in velocity would be the complete integral from 0 to 4, whereas change in speed is the area. So it'd be minus, because it's below, from 0 to 2, and then plus 2 to 4. Well, really, drawing velocity, acceleration, displacement graphs is nothing more than drawing derivative graphs, because that's what they are. So let's have a look at that in a little bit more detail. Function, the original function we'll call the displacement graph. The first derivative graph would be the same as the velocity graph, and the second derivative graph would be the same as the acceleration graph. All right, if we have a stationary point on our original graph, what does that tell us about the other two graphs? Well, we know stationary points occur when the first derivative is 0. So the velocity graph, well, I'm calling it an x-intercept. It'd actually be a t-intercept because our horizontal axis is time, but we get the intercept. If we had an inflection point, now an inflection point is where the second derivative would equal 0. Therefore, I have a stationary point on my velocity graph. Why? Because on the second derivative, I would have an x-intercept. And we can see from the level above this one that when we had an x-intercept, the graph above it was a stationary point. So the next level up, a stationary point. So if my second derivative has an x-intercept, the next level up, the first derivative, would be a stationary point. If the original graph is increasing, well, we know the curves are increasing when the derivative is positive. So we would have a positive, we'd be above the axis for our velocity graph. Similarly, if it's decreasing, well, then we would be below the axis on the velocity graph. Concavity, if the original graph is concave up, well, that means the first derivative, or velocity, will be increasing. Why? Because the second derivative is positive. So again, we can see that when the first derivative is positive, the next level up was increasing. So therefore, when the second derivative is positive, the next level up is increasing, so the first derivative is increasing. So original graph concave up, first derivative will be increasing, second derivative will be positive. And then we can do a similar thing for concave down. Original graph concave down, first derivative will be decreasing, the second derivative will be negative. What about the actual shape of the graph? We know that if we have a horizontal line is like y equals some constant. So if we integrate, we know we'll get an oblique line because you add 1 to the power over the power. So integrate a constant, you get a linear function. If you differentiate, you must now be on the x-axis because differentiate a constant, you get 0. If your graph is an oblique line, then when you integrate, you would get a quadratic function. So the shape would be a parabola. Differentiate an oblique line, you get a horizontal line. If the original graph is a parabola, when we integrate, we get a cubic. But what we saw before was it will have an inflection point at the turning point of the parabola. When we differentiate the parabola, we get an oblique line. Some other things to keep in mind. Remember, we said integration is basically finding the area under a curve. On a velocity graph, total area is the same as distance. Total integral is displacement. On an acceleration graph, total area is speed. Total integral is velocity. All right, let's have a look at this HSC question. So the velocity of a particle given by 2 minus 4 cos t and v is measured in meters per second, well, as most velocities are. At what times during this period is the particle at rest? Well, we know it's at rest when the velocity is equal to 0. So if I can solve that, cos t is a half. Well, we're in quadrants 1 and 4. We're only looking for answers between 0 and 2 pi. The acute angle would be pi on 3. So therefore, in the first quadrant, it's the same as the acute angle. Fourth quadrant, 2 pi minus the acute angle. So pi on 3 and 5 pi on 3. So that's when it's at rest, after pi on 3 seconds, and once again after 5 pi on 3 seconds. What is the maximum velocity of the particle? Now, we don't always have to use calculus to solve this sort of problem. We can use our knowledge of trig functions. We have a velocity graph which is 2 minus 4 cos t, but we know the amplitude of our cosine function. For this one, it would be 4. So that minus 4 cos t will travel between 4 and minus 4. But if we shift the whole thing up 2, it'll travel between minus 2 and 6. So the maximum velocity, 6 meters per second. Sketch the graph. So we just said the amplitude was 4 units. We're shifting it up 2, but it's minus the cos graph. So it'll flip upside down. Period 2 pi. I'll mark off my divisions every pi on 2. So let's draw up our axes. And you'll notice on the vertical axes, we just found out it travels between minus 2 and 6. So that's what I've labelled. I'll mark in a horizontal there for the axis of the curve. And let's see, normally we'd start a cosine curve up at the top amplitude, but this one's negative. So we flip it upside down. We'll start at negative 2. Then the cosine curve goes up to the axis, up then to the other amplitude, and now we'll come back down, and there's 2 minus 4 cos t. Calculate the total distance travelled. So total distance is the area. So we're going between 0 and pi. We've got a little bit that's below and a little bit that's above. So I'll have to split that one up. Now that x-intercept we worked out before was pi on 3. Remember the question said, when is the particle at rest? When is velocity equals 0? So we found, in effect, those x-intercepts, they're t-intercepts, but we found them. So all right, we know that it's pi on 3, but that's below. So from 0 to pi on 3, that will be negative. From pi on 3 to pi, it'll be positive. So we integrate. Notice on the first one, I have swapped the limits. So it's no longer negative. That means both of those functions, 2t, that means both of those functions are 2t minus 4 sine t. So when I sub in, I'll sub in 0 plus sub in pi, they're both the top ones, but then I'll take away twice when I sub in pi on 3, because the bottom ones are the same there. They're both pi on 3. Calculating that all out, well, a bit of a manipulation, but we get this wonderful answer of 4 root 3 plus 2 pi on 3 meters. Now, here's one where they gave us an acceleration time graph. They want us, from using this graph, to write down the time at which the velocity of the particle is a maximum. So how do we interpret this question? Remember, velocity would be the total integral of acceleration. So when is that integral going to be at a maximum? When is it going to have its largest positive value? Well, we know it'll be a maximum when t equals 2, right? Because it starts off up there at 3, and we're above, so that area is getting bigger and bigger and bigger and bigger, and we get to 2, but now it goes underneath. So I'm going to be taking away the area. So now it will become smaller and smaller and smaller and smaller. So the maximum must happen when t equals 2. Another way I could think of that is, I know velocity will be a maximum when its derivative is equal to 0. Well, its derivative is acceleration, and again, we can look at our acceleration graph, and clearly that's at 2. So whichever way you think about it, t equals 2. So at what time during the interval is the particle furthest from the origin? And this time they want us to give reasons for our answer. Okay, so our question is asking, when is displacement a maximum? When is it furthest from the origin? We know it's a maximum when dx to t is equal to 0. So when our velocity is equal to 0. But velocity, remember, is the integral of acceleration. So we're now saying, when is the integral of this curve equal to 0? When is the area above the axis equal to the area below the axis? Because that would give us an overall integral of 0. Because we have a lovely symmetric graph here, we know that's going to happen at t equals 4. Because the area above is going from 0 to 2. By symmetry then, 2 to 4 must be an equal area, but below. So t equals 4. Let's try another one. This one's a bit more interesting because we've got curves rather than straight lines. So objects moving on the x-axis, the graph shows the velocity dx to t, and the coordinates of the points they've given us there. So once we get to t equals 6, the velocity is constant. There's our horizontal line. Using the trapezoidal rule. Now actually in the HSC it said use Simpson's rule, but as that's no longer in the course, I've just modified our question here and made it the trapezoidal rule. Estimate the distance between 0 and 4. You see, we don't know the equations of those curves. So best we can do is come up with an estimate for the area underneath. So our trapezoidal rule will have h on 2, y values at the endpoint, so y0, yn, and then 2 times all the other y values. Draw up a table of values. Well, the only ones I know are when t equals 0, 2, and 4. So it'll be 1 time the end ones, 2 times the middle one. So we'll get h. Well, it's the height of each of our trapeziums is 2. And it'll be 2 on 2 outside of 0. Twice 1 plus 5, we get 7 metres. So that's our estimate of the distance that's been travelled between 0 and 4. They're telling us that initially it's at the origin. So during which time is the displacement decreasing? Well, we know it's decreasing when the derivative is less than 0. So dx to t is less than 0. In other words, displacement is decreasing when t is greater than 5. Well, how did I know that was greater than 5? Well, have a look at our graph. The area is positive when the graph is above the axis, and that goes from 0 to 5. Once it goes below, how do we know? Have a look at the graph. We're simply saying, when is this derivative graph negative? And it's underneath the axis once we get to 5. Displacement is decreasing when t is greater than 5 seconds. We're now going to estimate when the object returns to the origin. Once again, it's saying, when is displacement equal to 0? But we know displacement is the integral of velocity. So we're trying to solve the integral of velocity is equal to 0. So when is the area above equal to the area below? Well, let's have a look at this. Now, when's the area above equal to the area below? Just having a look at that straight line going from B to D. Well, that's symmetric. So the area from 4 to 5 equals the area from 5 to 6. So that little piece we know is equal to 0. Now we just estimated the area from 0 to 4 to be 7. So therefore, that rectangle that I've just shaded in, area 4 I've called it, we want to know when is that equal to 7, because then the area below will be equal to above. I'll have 7 plus the triangle, which would be the same as above the axis. We estimated the curved area to be 7, and we've got the triangle. So when is area 4 equal to 7? Well, I know that the height of that rectangle is 5. So I want to find the width of that rectangle. I've called it A. 5a is equal to 7. So solving that, we get A is 1.4. So therefore, particle returns to our origin when t is 7.4 seconds. We're now going to draw the displacement graph. So here's our velocity graph. I'll draw the displacement underneath. And I've marked in the key points on the time axis. So 2, 4, 5, 6, and 8. Object is initially at the origin, so I'll plot in the origin. Now we said that when t equals 4, x was equal to 7. So let's mark that point in. Now by symmetry, remember, the area of those triangles are equal, so we know that at t equals 6, it must be back at x equals 7. So the area of the triangle we can work that out. It's 2.5. So therefore, when t equals 5, x is 9.5. It returns to x equals 0 at 7.4. Now looking at my graph, I know that the velocity graph is steeper between t equals 2 and 4 than it is between 0 and 2. So therefore I know the particle covers more distance between 2 and 4. So I'll plot at t equals 2 the point less than halfway. Well, I might have exaggerated mine a bit. It's quite a fair bit low down. Now, when t is greater than 6, velocity is a constant. That means that x is a straight line. Integrate a constant, you get an oblique line. So I'll draw that in. And I'll continue the curve now. So there we go. You'll notice between 4 and 6, the original curve was a straight line. I've ended up with what looks like a parabola there. And I've just drawn a nice smooth curve going from 0 to 4. All right, let's look at one more. So once again, they've given us a velocity time graph. What time is the displacement a maximum? Displacement is a maximum when the area is most positive. So also when the velocity is equal to 0. So whichever way we do it, it's at t equals 2. At what times does it return to the origin? So when is displacement equal to 0? When is the area above the axis equal to the area below the axis? Okay, let's have a look at our graph. Well, from 0 to 1, we've got a rectangle, and I know the area of that rectangle is 2. Now, I don't know the area between 1 and 2. Let's just call it A for area. But by symmetry, it looks like from 1 to 3 would be the same. So we know they'll cancel. So I need to know when is that rectangle I've just drawn in equal to 2. Well, what is the width of that? Twice w must equal 2. So the width must be 1. So it returns to the origin after 4 seconds. This time they want me to draw an acceleration graph. So here's our velocity graph. So we're going to differentiate this graph. I'll draw it underneath again, marked in the key features. Differentiate horizontal lines. We'll get the x-axis, or in this case the t-axis. So I'll just draw those in there. So we know we're on the axis. From 1 to 3, well, it looks like a cubic. I'm going to assume that's a cubic. It inflects at 2, and it's decreasing. So then when I differentiate it, I'll get a parabola. It will be stationary at t equals 2, and it will be below the x-axis. From 5 to 6, well, again, it's looking like it's the same shape as from 1 to 2 and 2 to 3. I'm going to assume it is. So I'm going to say that's a cubic which inflects at t equals 6. And this time it's increasing. So when I differentiate, again, I'll get a parabola. It'll just be half of the parabola this time. It'll be stationary at 6, and it'll be above the x-axis. So there's my acceleration time graph. Have a go at these from 9C. See how we go.